Hello, everyone. My name is Kirill. I'm a PhD student at MIT advised by Guy Bressler, and today I'll tell you about our work on the Fourier coefficients of high-dimensional random geometric graphs. Let's begin with some motivation and background. Oftentimes, networks appearing in the sciences and in the real world form based on similarity of feature vectors. So, for example, in a social setting, people are friends because they have similar interests, live in the same location, or are the same age. If we want to theoretically study such networks, we need a convenient mathematical model. One such common model is given by random geometric graphs. Namely, in an n-vertex graph, every vertex has some random feature vector in a metric space. Then, conditioned on the feature vectors, an edge appears between I and j independently with some probability that only depends on the distance between the feature vectors. For example, the closer the feature vectors, the more likely for two people to be friends. However, oftentimes these feature vectors are only partially known or maybe even fully hidden. This could be due to privacy constraints in the social setting or simply because some information is not recorded. This gives rise to interesting statistical tasks. So, for example, if I just give you the adjacency matrix of a social network, can you recover some information about the feature vectors? Or I give you unlabeled noisy copies of the same graph. Think, let's say, the Facebook graph and the Twitter graph. Can you match the two graphs, meaning identifying the same person in the two graphs? There are also settings in which we care about inferring parameters of the underlying metric space, such as dimension. In this talk, I'll focus on a different statistical task, which is a simple hypothesis testing question. I give you a graph and I want you to decide, is it Erdős-Rényi or is it from some specific random geometric graph distribution? The intuition is that in Erdős-Rényi, every edge appears independently with probability p, so there is no underlying structure. And we can think of Erdős-Rényi as a natural null model. Of course, you may ask, why would I do this task? The first three tasks have very clear interpretations, for example, in social networks. But what about the hypothesis testing question? If I give you the Facebook graph, you already know that it's not Erdős-Rényi. I claim that there are a few different reasons. First, hypothesis testing is the simplest statistical task one can think of. More importantly, it is a prerequisite for some of the other tasks mentioned. If we cannot even distinguish our graph from pure noise, we probably cannot tell much more about the structure. Finally, there is yet another reason, which will be the motivating factor in this work, which is that developing or refuting testing algorithms reveals structure. So we learn something about the combinatorics or the geometry of the random geometric graph distribution that we study. Let's make things more concrete. We'll work with spherical random geometric graphs in which every latent vector is uniformly independently distributed on the D-sphere, and there is an edge between I and j whenever the inner product is more than some threshold chosen so that the expected density is p. The hypothesis testing question has been studied on random geometric graphs in the past nearly 15 years. Where we stand today is the following picture. Below some threshold, n cube, p cube, one can test between the two graph distributions successfully with high probability using signed triangles. For a second, forgetting about the sign. Why would one use triangles to test for geometry? It is because of the axiomatic triangle inequality of metric spaces. If A and B are friends, their feature vectors are close. If B and C are friends, their feature vectors are also close. By triangle inequality, we expect that the feature vectors of A and C are close, so we expect some prevalence of triangles. Subtracting the mean or taking the signed triangles is just a variance reduction technique that we will get back to. On the lower bound side, it is known that when the dimension is at least n cubed p square, then testing is information theoretically impossible. This was shown by Liu, Mohanty, Yang, and Schramm in 2022, and was also known in the very special case when the density p is constant from a prior work of Bobek, Keldan, Ratz, and Ding. The very special case when the density is on the order of 1 over n, it is known that a stronger information theoretic impossibility holds, which is that the two graph distributions are close even for a polylogarithmic dimension. Yet there is a gap. There is a gap between what we can do with the simple signed triangle counting test and the best information theoretic thresholds we have. And this gap has been open for nearly 15 years. In this work, we take a slightly different approach to this problem. Namely, we take a computational perspective asking about the strength of low degree polynomial tests. Notice that the sine triangle statistic just evaluates a degree 3 polynomial on the input adjacency matrix. So we ask, can we do something with other tests, perhaps of degree even log 1.1, which captures a broad, of course restricted, but broad class of polynomial time algorithms? We'll show that actually this is impossible, and to show hardness for low degree polynomials, it is enough to show that the following expression is the law of 1. Forgetting about the specifics of this expression, let's just focus on the expectation. For Erdős-Rényi, this expectation is 0 because every edge appears marginally with probability p, and the different edges are independent. Hence, this expectation is 0. However, for other graph distributions, for example, for random geometric graphs, this expectation maybe is different. And by looking at the magnitude, that's why we square it, and appropriately scaling, we can test between random geometric graphs and Erdős-Rényi. More concretely, to carry out this agenda and show that actually we cannot test using low degree polynomials, it is enough to bound the expected sign subgraph counts, which are also the rescaled Fourier coefficients. For certain models, such a computation is very easy and has been used over and over in the literature in the past 6-7 years. However, it turns out that for random geometric graphs, it is quite challenging, and actually bounding these subgraph expectations is the main result of the current paper. To illustrate the challenges and ideas, I'll focus in the next 10 minutes on the case of density 1/2 when the threshold is 0. Why is the threshold 0? Because two uniform independent vectors on the sphere have inner product more than 0 with probability half and less than 0 also with probability half. So what are some ideas for computing the Fourier coefficients? The first simplest idea is a direct integration. Just using the definition of random geometric graphs, we simply need to integrate the following function over the k-fold distribution over the sphere. However, this integration turns out to be extremely challenging, and after spending quite some time on it, I still don't know how to do it for anything, for any edge that is not a cycle or a forest. What about some approaches that people actually use for computing low degree Fourier coefficients? One very common technique is conditioning on the latent vectors. And I'll illustrate with a useful example of the planted clique. So in the familiar planted clique distribution, each of n vertices is included independently with some probability k over n in a set S. And then on the set S, all edges appear, so it's a clique, and all other edges appear independently with probability half. So how do we compute Fourier coefficients? Well, we condition on the latent vectors, which are the clique indicators. And now if a certain subgraph H has a vertex outside of the clique, it also has an edge for which at least one of its endpoints is not in the clique, hence the expectation is 0, because this edge is independent Bernoulli half. Otherwise, it's deterministically 1 over 2 to the number of edges. Integrating over the latent vectors or the clique, we get a very simple and convenient expression for the Fourier coefficient. However, such approach, even though very elegant and broadly useful, is impossible for random geometric graphs, simply because if we condition on the latent vectors, there is no randomness left. So if we know Zi and Zj, then the edge is also determined, and we cannot get this nice cancellation which occurs for the planted clique. A final approach which I want to mention is a perturbative analysis, similar to the cluster expansion, which Guy and me used in a recent paper, which also aims to bound the Fourier coefficients of a certain high-dimensional random geometric graph distribution. The difference is that in this distribution, the L-infinity metric leads to a factorization over different coordinates. And once we factorize over different coordinates and analyze the simple one-dimensional distributions, we can combine them using techniques similar to the cluster expansion. However, such a factorization does not occur in the spherical case. Hence, this approach is at the very least much more difficult to carry out. Okay, so we have three approaches, neither of which works. What do we do? Turns out that the planted clique example is very useful, but we need a slightly different perspective. Namely, our goal will be to represent random geometric graphs as planted subgraph distributions. In the planted clique, we have an ambient Erdős Shreni, and in it we add a uniformly located clique. In random geometric graphs, we'll aim to do the same. So we first start with an ambient Erdős Shreni, and then we plant a few edges which cause dependencies. And our main conceptual contribution is actually that random geometric graphs indeed have such a representation. And if we have such a representation, this will help us bound Fourier coefficients, right? Again, if a subgraph H meets a non-planted edge, so meets an Erdős Shreni edge, the Fourier coefficient is 0. So we'll get this cancellation and we'll get strong bounds. However, it turns out that the picture for random geometric graphs is not as simple. The true picture has some subtlety, which is in these boundary edges. So what's the description of random geometric graphs that we obtain? Again, we start by sampling an Erdős Shreni. Then we uniformly sample planted locations. So we include every location, think of it as a pair ij, independently with some probability gamma. But then whether we plant on these locations an edge or a non-edge depends on the Erdős Shreni edges in the boundary, meaning that we have some boundary, which is some subset of the edges adjacent to the planted locations. We look at what's on this boundary locations, and based on them, we decide whether there is an edge or a non-edge in the planted locations. So to recap, we have some planted pairs in which every pair ji is independently with probability gamma, and we also have some boundary, which is a subset of the edges incident to these planted pairs. And again, as long as the union of the planted and boundary pairs is not everything, we get the same cancellation as the planted clique, and we get the Fourier coefficient to equal 0. This means that if we should look at the minimal number of planted locations such that the plant locations and their boundary covers the entirety of H. If we have less than that number, then the Fourier coefficient vanishes. Using that the marginal edge probability is P and the appearance of each pair as a planted location is on the order of 1 over square root D, we obtain the following bound for the Fourier coefficients of random geometric graphs. Okay. Here, this OAI is the order H independence number of H. And to actually use this bound, we need to understand this combinatorial quantity, which depends solely on H. So let's go to applications, and specifically we'll start with the first motivating application, namely testing between random geometric graph and Erdős Shreni. Our first bound on this order H independence number is that it is at least the number of vertices over 2. And this immediately gives the following complete low-degree harness. So below some threshold, we can detect using signed triangles, and above some threshold, the testing problem is hard for low-degree polynomials. So we have a tight characterization of what low-degree polynomials can do. And by low-degree, I mean degree log 2 minus epsilon. It turns out that the strength of signed triangles extends even beyond this setting. In a recent work, Mardu, Verschand, and Wine introduced the non-adaptive edge query model for low-degree polynomials, in which instead of observing the full adjacency matrix of a random geometric graph, one observes a subset of the edges, so queries a subset of the edges of a potentially even larger graph. What is the idea? The input to low-degree polynomials are edges. Hence, by taking a more structured set of edges, one can potentially obtain a more data-efficient algorithm, which uses less edges, maybe on more vertices, but it's still less edges, so less data. Turns out that this is impossible for the testing problem between random geometric graphs and Erdős Shreni. Again, below the threshold, some threshold, we can test using signed triangles on the complete graph, so we just observe everything. And above this threshold, the two graph models are low degree indistinguishable, even in this more general non-adaptive edge query model. And here I must say that one of the key insights is that, so for each set of queried edges, we need to bound how many copies of a certain subgraph there appear. Such a bound is given by a paper of Alon in the 80s, and it's very tightly related to the following combinatorial quantity, which is the maximal difference between a vertex set of H and its neighborhood set. Magically, we show that our ordered edge independence number is at least this quantity plus 1, which is the main workhorse behind this result. So far into different applications, we show that sine triangles are the most informative low-degree Fourier coefficient for random geometric graphs. This has the following conceptual implication. Take some completely different model with the property that again sine triangles are the most informative Fourier coefficient. Now, if we match in this other model, the sine triangle count and the sine triangle count in random geometric graphs, maybe the two distributions are low-degree indistinguishable. That's exactly what we do. So we take the planted coloring model from a recent paper of Kothari, Wine, Zhou, and Vampola. So what is this model? It is, again, we have an ambient Erdős-Renyi, and we plant cliques, except that we don't just plant one clique, but we partition uniformly the vertices into Q cliques. And we test this model against against random geometric graph. We show that in some regime for the dimension, there always exists some value of Q such that the detection this distinguishing problem is with respect to low-degree polynomials. And know that this actually constitutes an information computation gap, because for some non-trivial regime of D, the largest clique in the planted coloring model is n over Q, which is of polynomial size. However, in random geometric graphs, it's only of logarithmic size. So there is a test that distinguishes the two graph distributions, the size of the largest clique, but this test is computationally efficient. We also remark that we get hardness in the same regime in terms of Q as the refutation hardness in the paper of Kothari, Wine, Zhou, and Vampola. We have a few other applications on spherical random geometric graphs and Gaussian random geometric graphs. We even show some surprising, perhaps, difference between the two models. But I will end here and just pose a few open questions. So, of course, the elephant in the room is the information theoretic convergence of random geometric graphs to Erdős-Renyi. When can we test between the two models? And this question has been open for the past 13 years, even though there has been gradual progress. Here I propose a few other questions. So first, one of the conceptual contributions of our work was this planted subgraph view of random geometric graphs. Can we find other applications? Likewise, can we produce such a representation in other geometries? So going beyond spherical random geometric graphs, is there such a planted subgraph representation? Then we upper bounded the Fourier coefficients, which was useful for low-degree hardness. However, if we actually want to use these Fourier coefficients for inference algorithms or estimation, then we actually need precise estimates or even lower bounds for the Fourier coefficients. So how do we obtain those? Finally, all of our hardness results are against degree log 2 minus epsilon polynomials. Can we do something stronger? Can we do log 2 plus epsilon, or maybe even a polynomial degree? And I should say that this is a partial step towards the information theoretic bound, because the information theoretic bound is essentially against degree n choose 2 tests. Thank you.